So,
If you look at the redox chart, do you see perchlorate on the redox chart? Perchlorate, what would you characterize perchlorate as?
base.
For redox. An oxidizer or reducer? Electron rich or electron poor? Electron poor. Very poor or not so poor? Very poor, which means it's going to be a what? Strong oxidizer. It's going to be a powerful oxidizer, but is it on the chart? So, you know, when the student asks me, do I need to memorize it? Well, it depends on how you memorize it. If you memorize it and you go, hey, I memorized that perchlorate's not on the chart, therefore perchlorate is insignificant. Is that? No, that's worthless. And so, yeah, in that sense, memorization is worthless because you don't know anything beyond what you've memorized. But if you know something beyond what you've memorized, like perchlorate's going to be in this region here. It's some pretty dangerous stuff, you know. So it fit right in this region of powerful oxidizers. And so this is why we want a little bit more, you know, a little bit more knowledge than just straight memorization. But you have to do some straight memorization to gain that knowledge, to memorize some stuff. So you memorize some of the familiar faces or names of the powerful oxidizers, what they have in common. H plus can react with silver metal. This is single replacement. It doesn't fit the single replacement form, but it is. It says it's a redox reaction. 11. Magnesium ions and hydroxide ions will precipitate. Hydroxides in general precipitate unless they're with group 1, ammonium. Not group 2, not all of group 2, just group 1, ammonium and calcium, strontium, and barium. Magnesium is not one of the exceptions, so yes, this is true, it precipitates. 12, the mass of carbon-13 is exactly 13U. That you have to have memorized. That would be mass of carbon-13 is exactly 13U would be true or false? Carbon 12, right? That's false. This is false. This is carbon 12. Wrong. It's close, but it's not exactly. 13. An element has two isotopes, 6U and 7U. The 6U is 10% abundant, 7U is 90%. And so what's the average? The average is going to be much closer to 6 or much closer to 7. It's going to be much closer to 7. 90 out of 100 weighs 7. Only 10 out of 100 weighs 6. And so the average will be 6.9 B. Or you could use the equation if you want, or you could do it graphically. You know, when I see the problem like this, I just visualize the scale like that. You know, if it's 100% 6, isotope 6, element 6, then it weighs 6. If it's 100% 6, then 0% 7. And so the average weight is going to be 6. Likewise, if it's 0% 6, it would be 100% 7. If it's 100% 7, then it's going to weigh, the average is going to weigh 7. If it's 50-50, you know, 50-50, 50% 6, 50% 7, it's going to weigh 6.5. But in this case, it's 90% 7. If it's 90% 7, it's going to weigh 6.9. So it's going to be 90% of the weight of 7. So 6.9. It's one way to do it. Other way is just put it in the algebraic equation and solve for the average. 14. No object exists that weighs exactly 1 U. If it's false, what object weighs exactly 1 U? Carbon-12 doesn't weigh exactly 1 U. That's why I don't like that definition. The definition is, they say 1/12 of a carbon-12 atom weighs exactly 1 U. But how can you get 1/12 of a carbon-12 atom? Is that possible to slice it into 12 even pieces? No. And so it's impossible. There's nothing that weighs exactly 1 U. And so the way I like to define it is a single atom of carbon-12 weighs exactly 12 U. There's an object that weighs exactly 12 U, and that's a carbon-12 atom. But there's nothing that weighs exactly 1 U. And so the definition of U is not based on 1 U. The definition of the U is based on 12 U. 15, mass number is not mass. That's true. Mass number is what? Yeah, the number of protons plus the number of neutrons. It's a number, it's not a mass. It's going to be close to the mass. It's close to the mass because neutrons weigh 1 U, about. Protons weigh about 1 U, and electrons are negligible. So the mass of the atom is close to the mass of the proton plus the mass of the neutron, which is close to the number. 16, U-238 contains how many neutrons? 146. Actually, yeah. Because uranium's 92, element 92. Here. So uranium's element 92, which means it has 92 protons. So 92 plus blank gives 138. So 92 plus 146 gives 238. So the correct answer is C. That's good. How many water molecules are in one drop? 0.05 milliliters of water. Do you calculate this one?
I tried to. I kind of wrote it out, but then I didn't get an answer choice. I got 1.67 times 10 to the 21st. And the closest thing was C, but it was really far around, so I didn't think I did it correctly.
Okay, you did it correctly. Well, 0.05 milliliters. How do you know if you did it correctly or not? Because this is a test. There's no answer key. How you know you did it correctly is you make sure you write out the units. And the units cancel out properly. And most likely you did it correctly. And then you just double check your calculation. So this is 0.05 milliliters of H2O. And then where did you go?
Grams.
Grams. So what did you use? 1.0 grams of H2O per milliliter, 1 milliliter of H2O. That's the, what do we call that? The density of water. And everybody should know the density of water. The density of water is just 1, right? To 3 sig figs, 2 or 3 sig figs. To 4 sig figs, we better look it up in a table. So 1.00 grams of water per 1 milliliter of water. So we have 0.05 grams of water. And then where did you go? Moles. So we need the molar mass of water. Yeah, oxygen is 16.00. And we have 2 hydrogens. Each hydrogen is 2 times 101. This gives us 18.02 grams per mole. So 1 mole of water weighs 18.02 grams. So the grams of water cancels. That leaves us with moles of water, and then where did you go?
Molecular
to the number of molecules. So we need Avogadro's number. You have to have it memorized at 4 sig figs. What is it?
6.022.
Yeah, 6.022 times 10 to the 23rd molecules per mole of molecules of H2O. Yeah. So units work out, and we just double check the calculation here. .05 divided by 1802 times 6.022 times 10 to the 23rd. 1.6709 times 10 to the 21st. Okay, how many sig figs am I allowed? I'm only allowed 1 sig fig here. So if this is 1 sig fig, I have to round it. It's going to round to 2. 2 is a huge error, though. How many billions and trillions of molecules am I off by? I'm off by a huge number of molecules, because this is times 10 to the 21st. So I'm off by 3 times 10 to the 20th. Molecules is huge, roughly. But anyway, we got to live with this round-off error. So 2 times 10 to the 21st. C. 18. The cathode ray tube was used to discover the electron. And true? No? What was used to discover the electron? If it wasn't the cathode ray tube. The what? The Crookes tube is the cathode ray tube.
Okay.
Crookes tube and cathode ray tube are the same thing.
So
True. Yeah, it's true. CRT, Crookes, etc., etc. These are all synonymous with cathode ray tube. CRT. Up until not so long ago, televisions operated by cathode ray tubes. Water contains 1/3, 33.3% oxygen by mole. False? What do I mean by mole? If I look at it by atom, does water contain 1/3 oxygen by atoms? 1/3 of the atoms are oxygen. There are 3 atoms total. 2 hydrogens, 1 oxygen. So 3 atoms total. 2/3 of the atoms are hydrogen. 1/3 of the atoms are oxygen atoms. So what I mean by mole is this. A mole is just a counting unit. So if I have 3 atoms, then 1 out of the 3 atoms is oxygen, 2 out of the 3 atoms is hydrogen. What if I had a dozen? Let's say if I had a dozen of these molecules, 2 dozen of the atoms would be hydrogen, and 1 dozen would be oxygen. And so we could say that water is 1/3 of a dozen, by dozen, 1/3, or 33% by dozen. Well, mole is just another counting unit. So if I had a mole of water molecules, I had 2 moles of hydrogen and 1 mole of oxygen, just like a dozen. And so this is true, actually. By mole, it's 1/3 or 33.3%. By mass, it isn't. This ratio is a mole ratio or an atom ratio. It's not a mass ratio. this doesn't mean they're 3 grams. In 3 grams of water, it's not 2 grams of hydrogen and 1 gram of oxygen. Formulas are mole ratios or atom ratios or dozen ratios. It's 2 dozen, 1 dozen. So, by mass, it's a totally different story because oxygen weighs so much more. It's 89% oxygen by mass, 11% hydrogen by mass. CO2, number 20. CO2 can be combusted further to form CO3. No, it looks like the consensus. This is false. CO2 cannot be combusted further to form CO3. Why do you say it that? Why can't they? I've seen CO3 before.
Come out of CO2?
I've seen CO3 before, but it looked just a little bit different. I've seen CO3 2 minus. This one is called carbonate. This one would be called carbon trioxide. So this is carbon trioxide, this is carbon dioxide. It's different. It's not carbonate. It's carbon trioxide. And so why do you suspect we cannot form carbon trioxide?
Only go to +4.
What?
You can only go to +4.
You can only go to +4. Carbon trioxide would be +6. You'd have a very, very unhappy carbon. Because carbon is element number 6. Element number 6 has how many protons? Element number 6 has 6 protons and 6 electrons. If carbon were +6, it'd have to lose every single one of its electrons. Is that going to be easy to do? No. So carbon +6. Carbon +6 is, yeah, so unstable, so difficult to do. We don't expect it to happen. So we don't expect carbon trioxide to happen. You know, that range holds pretty good. Unless it's a very exotic species. Have you seen any exotic species that went outside that range of charge? Yeah, as a matter of fact, we saw one yesterday. What was it? Which one was it? Ozone? No, ozone is within the range. Oxygen ranges from, technically it ranges from +6 to -2. That would be the range for oxygen. Ozone is, ozone. Ozone should be 0, what it should be. But ozone is, not all the oxygens are the same in ozone. So that's why it's a little bit more tricky. What's this one? Sulfate. What's the charge on sulfur and sulfate? Well, the charge of the sulfate ion is 2 minus. If we look at the oxygens in sulfate, it would be -2, and the sulfur would be +6. So we have sulfur in the +6 in sulfate. Normally the 8s are maxed out. The 8s have the maximum number of oxygens that we're going to see. The only time that didn't happen was with chlorate. With chlorate, they named it too early. With chlorate, they thought it maxed out at 3 oxygens, but it actually maxed out at 4 oxygens with perchlorate. Perchlorate maxed out, and so they had to come up with a per. But is there such thing as a perchlorate? A perchlorate would be 5, maybe ClO5 minus. Perchlorate, no. But this is kind of weird. This might be like a persulfate in this case, you know, because the sulfate's maxed out. Normally it's maxed out, like carbonate's maxed out. But this sulfur is very odd. What is this sulfur? +7. That's very odd. And it's not a common species. It's a very exotic species. This is number 3 here. Sulfur should max out at +6. It maxed out at +6. So we aren't going to ever deal with this species here.
Ozone, yes. Fluorine, yes. Hydrogen peroxide, yes, but not this.
Really? So carbon trioxide, false. 21, the oxidation state of chlorine varies from -1 to +5. False. Yeah, -1 to +7. When aluminum is oxidized, AlO2 is a potential product. False. AlO2 is not a potential product. Why? Two and 3. Al2O3. Al2O3 is possible, but this is not. This is not possible because
The charge is not balanced.
the charge is balanced. Well, aluminum would have to be what charge in order for this to work? +4. Is +4 possible for aluminum? No, we don't expect it. +3 should be its max positive. If a species like that formed, it would be very unstable. A carbon-12 atom in methane weighs exactly 12 U.
False.
True. This is true. All carbon-12 atoms weigh exactly 12 U, no matter where they are in the universe. It could be anywhere in the universe, they're going to weigh exactly 12 U. The reaction F2 plus NaI fits a single replacement. Okay, single replacement, let's skip that. Would it be true? It's false. This is false. This is one of the exceptions. I haven't talked about the exceptions yet. I'm going to talk about those tomorrow. This one does not fit a single replacement pattern. Lots of people try to force it to fit.
A plus Bx. F2 plus NaI. A plus Bx yields AX. Plus B.
It doesn't work. I'll talk more about it later. Or you can get all kinds of weird stuff. I mean, it fits the pattern, yes, it's an element plus compound, but it doesn't fit the pattern because the pattern is very specific. The pattern is very narrowly defined to make it easy. So we're going to skip it for now. 25, gas formation is driving force for redox.
False.
That's false. Gas formation is the driving force for what type of reaction? Metathesis. 26, a compound containing 82.7% carbon and 17.3% hydrogen contains, it has a mass of 58 U. Determine the molecular formula. 26 is okay. 27, write the balanced equation for the complete combustion of methane. 27 you can skip. Not having the combustion on that. 28A, lead metal and hydrochloric acid. This is a single replacement. 28A, skip that. 28B, acetic acid and calcium carbonate. That is double replacement, do that. 28C, barium nitrate and ammonium sulfate, double replacement, do that. 29A, carbon is burned in air. Carbon is burned in air is an element plus element combination. That forms different products. For example, incomplete combustion will form carbon in the +2. Complete combustion will form carbon in the +4. So we have multiple products here. And so when we have a choice of multiple products, usually we'll go complete. Usually we go complete unless the chart tells us we don't. And so in this case, I would probably go completely to CO2. B, sodium metal and aqueous potassium chloride. Now that's a single replacement, so skip B. 30, I might not make this a bonus, like write the solubility rules. I might not make that a bonus and just make that a part of the test. I give some a little bit of bonus here. What are the chemical properties of HNO3? Well, you aren't going to have that type of problem because we haven't finished talking about chemical reactions yet. You will have this type of thing. Write the solubility rules. Can you write the solubility rules? All right, that's pretty much the test. Were there any specific questions from this test or the homework or from lecture that you want me to go over?
I had a general question. It was about the single replacement one, but it was about looking at the chart for like the charges. So when I tried to work out 28, and I was trying to put it into the products, I thought that it was lead to. I just want to know if I was reading the chart correctly.
Yeah, you're reading the chart correctly. You're talking about lead metal?
Yeah, because it goes from lead solid, and then I got lead to.
Yeah, that's what's going to happen. And so when you look at the chart, like I said, normally we do it completely. So there's two charges for lead. There's lead 2 and lead 4. And so normally we would take it to lead 4. That would be complete, what we call complete oxidation, complete combustion, whatever. But in this case, the chart tells me I go from lead to lead 2, not lead 4. The same thing with tin. Tin doesn't go all the way to tin 4, it just goes to tin 2.
Will that always be the case? Just by 2 first, unless it says 3?
No, it's not always the case. For these, it's always see, for these it stops part way, it doesn't go all the way. For copper doesn't stop at +1. Copper goes all the way to +2. You know, copper is a +1 and +2, so it goes all the way. In other words, it's completely oxidized, +2. Whereas tin and lead are only partially oxidized. And so what I'm saying is, if it's not specified, we're going to completely oxidize it if it's not specified. And so the question here is, we should take lead all the way to lead 4. However, the chart says otherwise. We take lead to lead 2. And so we're going to go with the chart. Otherwise, if it's not on the chart, I would take it to lead 4.
Other questions. When you're trying to show the driving force and you have a precipitate, like where do you draw the arrow from?
You draw the arrow directly to the precipitate. So if there's a precipitation, that's the driving force. Like for example, we could do a precipitation here. Barium nitrate. Barium nitrate. What's the formula for barium nitrate? Plus ammonium sulfate. NH4 2SO. SO4. A double replacement style reaction. So we're going to get barium sulfate and ammonium nitrate. Sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium. Barium is an exception. So barium is not soluble to the precipitate. And so what I do is I do this, DF, PPT, and then point to the precipitate. That's how I'd show the driving force. DF stands for driving force. This would be the CE. I also want the IE and the NIE. So I want the CE, driving force, IE, NIE for each of these. And so for the IE, we ionize just the strong electrolytes. The strong electrolytes would be the strong acids, strong bases, and soluble salt. So it's barium nitrate, strong acid? No. Is barium nitrate a strong base? No. Is it a soluble salt? Yeah, all nitrate salts are soluble. And so we're going to ionize it into barium ions, and for every barium we need 2 nitrates to balance it. We're going to make sure we have the charges shown. Ammonium sulfate, strong acid? No. Strong base? No. Soluble salt? Yes, all ammonium salts are soluble. And so we're going to get 2 ammoniums for every sulfate. That should be balanced. Don't forget the charge. Charges. I'm sorry?
Would it be 4 because you didn't balance?
No, I didn't balance it. You're right. 1 barium, 1 barium. 2 nitrates, so I need 2 ammonium nitrates here. And then 2 ammoniums here, 2 ammoniums there, 1 sulfate, 1 sulfate. So now it's balanced. For what? Okay. Barium sulfate. Strong acid?
No.
Strong base?
No.
Soluble salt?
No.
No. So if it's none of those, then just leave it alone. Barium sulfate should just be left as is. Ammonium nitrate. Strong acid?
No.
Strong base? Soluble salt? Yes, soluble salt. So it's going to break apart into 2 ammoniums. And for every 2 ammoniums, we'll need 2 nitrates. So 2 ammoniums and 2 nitrates. And then the NIE, what are the spectators here? Barium ions? React. Nitrate ions? Yeah, they don't react, they're spectators. Ammonium? Spectator. Sulfate? No. And so the reaction is barium 2 plus sulfate, SO4 2 minus, yields BaSO4. What type of reaction is this? Metathesis. Metathesis reactions are favorable ion combinations. If I just look at the favorable ion combination here, does this look like double replacement to you? When I think of double replacement, I just think of double replacement as a fancy name for just seeing which pairs of ions like each other. Double replacement is just a fancy name for just swapping the anions. So you would take this ion from here and move it over here and see, do they like each other or they don't like each other? You know? So I don't think of double replacement as being necessarily a reaction. I think of it as just being a tool for just figuring out different ion pairs. That's all. The actual reaction are the ion pairs themselves. So this is why I call it metathesis, and I don't use double replacement that much. But double replacement's kind of handy because, you know, we can just figure out if I take barium ions with sulfate ions, is that a good pair? And if I take ammonium ions with nitrate ions, is that a good pair? No. And so, but this is what I call metathesis. This is not what I call double replacement. Double replacement is that tool to figure out what ions like each other. And once we find out what ions like each other, then we'll just focus on that. The other ions aren't interacting at all. They're spectators. Uh-huh.
Do we have time for a Bronsted example?
A Bronsted example? A Bronsted example is if you get like no reaction. Like a B is both. This reaction B is both acid base and double replacement or metathesis. If metathesis works, use metathesis. Because Bronsted is more hassle. Some people will say, do I have to learn all 7 steps for the Bronsted method? Yeah, but it's not that hard because you don't do them separately, you do them all at once, so it makes it a lot easier. And so this is an acid-base reaction. I know acetic, what's the acetic acid? HC2H3O2. It's acetic acid. And then calcium carbonate? CaCO3. I know this is a Bronsted acid-base reaction. How do I know? Because I know acetic acid is an acid. If acetic acid is the acid, what's the base? I'll tell you what the base is. The base is carbonate. Carbonate's the base. But we're not going to do it. We're not going to do Bronsted like this because if double replacement works, I'd rather do it that way. That is, I'd much rather do hydrogen ions with carbonate ions. Hydrogen ions with carbonate ions makes what formula? Well, it makes how many hydrogens, how many carbonates? 2 hydrogens and 1 carbonate. We call that carbonic acid. Carbonic acid, is it stable?
No,
It decomposes into CO2 and water. CO2 gas plus water. This is one of those ones you just have to memorize. Like carbonic acid, what was the other acid? You just talked about it? Acetic acid? No, I mean the other unstable one. Hydrosulfuric acid is somewhat stable. It doesn't decompose. It just comes off as a gas. With sulfurous acid. Yeah, and then well, we're gonna well, sulfurous acid is H2SO3. What we're gonna form here is calcium ions with acetate. Calcium with acetate is calcium is a 2+ acetates of 1-, so we'll need 2 acetates for every calcium. Yeah. Is there a driving force for this reaction? Yeah, there is. What is it? One is gas formation, so what I do is I just point to CO2 and just say gas. Just write TF, gas. There's one more driving force. The one more driving force is acetic acid versus carbonic acid. Which one's stronger? So we could take a look at the chart here and see. Acetic acid versus carbonic acid, I would say that, and here I'd have to look at the chart because I don't have it memorized. I'd say here's acetic acid, here's carbonic acid, so which one's stronger? Acetic acid stronger. So we're going from stronger acid to weaker acid. Now there is something that is kind of different about this particular reaction here. Because acetic acid, is that soluble or insoluble? Soluble, group 1, so it's aqueous. Calcium carbonate, is that soluble or insoluble? It's insoluble. Carbonates are all insoluble except for group 1 and ammonium, so this is a solid. So what we have is we have the reverse. We're destroying a precipitate. We're destroying a solid, so it's anti-precipitation. We're taking a solid precipitate and destroying it. And so that's maybe favorable, maybe not so favorable in this case. But all we need is one driving force. Here we have 2 driving forces. The 2 driving forces, stronger acid, the weaker acid, and gas formation. And so if we have driving force, we should balance it. So we'll need 2 acetic acids to be balanced. All right, but what's going to happen is sometimes what you'll do is you'll go through these and you'll get no reaction. If you get no reaction, you shouldn't give up. Maybe there is a reaction. how many other types of reactions do we have to worry about? So let's say we got no metathesis reactions. Do we have to worry about an infinite number of possible reactions that are unforeseen, unseen? No, we just have to worry about if metathesis doesn't happen, then maybe acid-base happens. If acid-base happens, then we treat this differently. So the thing is, this reaction works by metathesis, so just use metathesis. But if it didn't work by metathesis, what we'd have to do is we'd have to do this. We'd have to do the Bronsted method. The Bronsted method is step one. What do we do? We inventory. What's the inventory here? Well, acetic acid, does it break apart or does it stay together? It doesn't break apart, it stays together. It's a weak acid, only strong acids break apart. Calcium carbonate, does it break apart or stay together? It stays together, and water. This is it. And so we look for reactions here, like that. This one is more difficult, more complex. I'd give you a simpler one, like the ones I gave you in class. So take a look at the ones I gave you in, well, the one I gave you in class. Actually, I gave you two. I gave you two Bronsted acid ones. Take a look at those. Analyze those. I can do another example if you want tomorrow, beginning of lab. We're out of time now, but tomorrow.